In the pre-dawn darkness over Baghdad, 2 F-117 Nighthawk aircraft.
त्यांच्या रूपाने सपाट कोनीय विमानांचा धबधबा त्यांच्या लक्ष्याजवळ पोहोचला.
Below, sophisticated radar-guided surface-to-air missile batteries scan the sky.
Searching for the electromagnetic signature of an impending attack.
They detected almost nothing, perhaps a small, transient blip.
Indistinguishable from background noise, just before the Nighthawk's payload bay doors opened. With their munitions delivered to the presumed location of Saddam Hussein.
The F-117s, their locations potentially compromised, turned swiftly to exit hostile airspace.
This aircraft was a paradox. It possessed the silhouette of a fighter, but lacked any of its defensive or offensive air-to-air capabilities. As a subsonic platform armed only for ground strikes, it was utterly defenseless against enemy interceptors.
Its sole defense and its entire operational doctrine was an unprecedented reliance on stealth.
A concept it would validate by striking 1,600 high-value targets during the Gulf War without a single loss.
This revolutionary aircraft was not born from a desire for a better fighter, but from an existential crisis.
The balance of air power had been fundamentally overturned during the 1973 Yom Kippur War.
In just 18 days, Israeli forces, flying the most advanced American attack aircraft of the era, lost 109 planes, primarily to Soviet-supplied SAM systems.
These systems, vastly cheaper than the aircraft they destroyed.
Required crews with only a fraction of the training needed for a combat pilot.
The strategic implications were staggering. Air Force planners, extrapolating these attrition rates to a potential conflict in Eastern Europe.
Reached a chilling conclusion. The entire United States Air Force could be annihilated by Soviet defenses.
We must accelerate the timeline if we want to meet the deadline.
The simulations are running at full capacity, Colonel.
In approximately 17 days.
This new reality rendered the existing playbook of high-speed, high-altitude bombing obsolete.
And catalyzed a desperate search for a counter-strategy. In response to the escalating SAM threat, conventional wisdom pointed toward a strategy of avoidance.
This path led to the development of aircraft like the B-1 Lancer.
A marvel of engineering, designed to execute long-range missions at extremely low altitudes.
Hugging the terrain to hide from radar in the ground clutter.
Its variable sweep wings provided the aerodynamic flexibility for both low-altitude dashes and high-altitude cruise.
However, a far more radical solution was germinating within the classified halls of Lockheed's Skunk Works.
The key arrived not as an engineering blueprint, but as a Russian scientific paper.
The document, filled with complex mathematical theory, had been published internationally, its true significance apparently lost on the Soviets.
For Overheiser, the paper was a Rosetta Stone.
It unlocked a method for calculating the diffraction of electromagnetic waves, a problem previously thought too complex to solve.
Stealth design until that point was not new. The SR-71 Blackbird, for instance,
Incorporated basic stealth principles based on physical optics, and the avoidance of corner reflectors.
This, however, was a quantum leap.
Diffraction explains how waves bend around an obstacle,
allowing the energy of the sea to find its way into a seemingly protected harbor.
Overheiser's paper provided the mathematical tools to model and, therefore, control this phenomenon for radar waves. Ben Rich approved the development of a computer program, dubbed Echo 1, which, within 3 months, could analyze the radar cross-section of simple shapes.
From this program emerged a simple, diamond-like shape that aerodynamicists at Skunk Works wryly named the Hopeless Diamond.
The transformation of the Hopeless Diamond from a theoretical radar-deflecting shape into a functional aircraft
required a complete inversion of the traditional design process.
Instead of aerodynamics dictating the form was now dictated by the unyielding mathematics of radar invisibility.
The aircraft's mission was defined as a precision bomber, eliminating the need for external hardpoints, which would catastrophically compromise its stealth profile.
Yes. It would carry just 2 internal laser-guided or GPS-guided bombs.
This internal-only carriage, combined with the need to avoid the sonic boom and reduce aerodynamic heating,
both of which could be detected, cemented the F-117 as a subsonic aircraft.
This simplified engine selection, leading to the adoption of the General Electric F-4004 engine.
A reliable and maintainable non-afterburning turbofan.
The greatest engineering challenge was integrating this propulsion system.
An engine inlet is, by its very nature, a massive radar-reflecting cavity.
The solution was as unique as the aircraft itself. The inlets were shrouded by a faceted structure and, crucially, covered by a radar-reflecting grid.
The spacing of this grid, a mere 1.5 centimeters, was precisely calculated
to impede the passage of radar wavelengths, which are larger than the gaps. While this mesh effectively hid the engines from radar, it introduced severe aerodynamic penalties.
It drastically reduced pressure recovery, the measure of air pressure available to the engine, thereby choking its thrust. To compensate, secondary intake doors were added to provide sufficient airflow at low power settings, such as taxiing.
These doors were programmed to close automatically as the plane accelerated past Mach 0.5.
This grid also created a massive icing hazard. Unlike small pitot tubes, it could not be easily heated.
The solution was a system akin to a windscreen wiper. Which would emerge from the inlet lip to spray a glycol-based anti-icing fluid.
Just as the engine inlets presented a radar challenge, the engine exhaust posed a dual threat.
Radar signature and, just as critically, heat signature.
An infrared-guided missile could be just as lethal as a radar-guided one. The F-117's engineers were tasked with cooling the exhaust and diffusing its heat signature as rapidly as possible.
Their solution was the platypus tail, a long, flat extension of the fuselage.
The engine's round turbine exhaust was transitioned into a flat, 17:1 aspect ratio rectangular duct.
This thin, wide shape spread the hot exhaust over a larger area, allowing it to mix more quickly with ambient air.
Furthermore, the fuselage extension below the exhaust was lined with heat-absorbing ceramic tiles,
which were actively cooled by bypass air siphoned from around the engines.
This design effectively masked the Nighthawk's intense heat from prying infrared sensors below.
However, this radical exhaust system produced unforeseen and dangerous aerodynamic consequences.
We're losing control. Stabilize the yaw.
Which were discovered during the Have Blue demonstrator test flights.
Okay, flooding tactics array.
The thrust from these angled, flattened nozzles was not perfectly symmetric. The thrust vector between the two engines could differ by as much as 8 degrees, particularly during side slip. This differential thrust would push the plane sideways.
The Have Blue's flight computer used a lateral accelerometer to detect side slip.
But this asymmetric thrust caused the accelerometer to register a false side slip reading.
The computer would then try to correct for a side slip that did not exist,
which in turn created actual side slip, which then increased the asymmetric thrust.
Warning.
Warning!
This created a dangerous positive feedback loop of instability.
The problem was only solved by replacing the accelerometer's data with input from a beta vane,
A physical sensor that measured the actual relative wind,
allowing the flight computer to distinguish between true side slip and thrust-induced yaw.
while the propulsion and exhaust systems were engineering marvels of signature reduction.
The F-117's wings represented the greatest compromise.
In a conventional design, an aerodynamicist carefully selects sweep angle, airfoil, and wing area to maximize lift, minimize drag, and ensure stability for the aircraft's intended speed and altitude.
For the F-117, these choices were almost entirely out of their hands.
The Echo 1 program dictated an extreme wing sweep of 67.5 degrees.
This was a sweep angle appropriate for a supersonic interceptor, not a subsonic bomber flying at airliner speeds.
This extreme sweep, necessary for stealth, produced significantly less lift than an equivalent unswept wing. This problem was compounded by the airfoil itself.
A normal airfoil is a smooth, curved shape designed to create a clean pressure differential.
The F-117's airfoil was composed of simple, flat facet plates, 2 on the bottom, 3 on top.
This shape created pressure peaks at the facet lines,
resulting in a very poor lift-to-drag ratio and introducing issues with aerodynamic flutter.
To compensate for this inherent inefficiency, the designers were forced to give the F-117
a massive wing area of 72 square meters.
For comparison, the F-15 Eagle, an aircraft renowned for its low wing loading and maneuverability,
has a smaller wing area, despite having a higher maximum takeoff weight.
The F-117 simply needed an enormous wing to generate barely enough lift.
This design also created pitch instability on the Have Blue demonstrator,
which could not pitch down if its angle of attack exceeded 17 degrees.
This led to a test flight crash when a control surface on the platypus tail deployed automatically.
Just 1 meter off the runway, slamming the aircraft into the ground.
Consequently, the final F-117 design featured a more stable V-tail acting as rudders, and large, full-span elevons to ensure adequate control authority where the Have-Blue had failed.
The culmination of these extraordinary engineering compromises was an aircraft.
That was aerodynamically unstable, difficult to fly, and defenseless.
Yet, in its intended role, it was invincible.
Operation Desert Storm was its ultimate vindication.
The 36 F-117s deployed to Saudi Arabia flew missions over the most heavily contested airspace in Iraq with impunity, systematically dismantling the nation's air defense system.
On the first night alone, they struck 26 high-value targets.
The F-117 rendered what was once a Soviet trump card.
The program's value was summarized by the Air Force.
A standard pre-stealth attack package costs $6.5 billion over 20 years.
The stealth package, requiring only the F-117s and tankers, cost $1.5 billion.
The Air Force, however, was fully aware that this golden period would be short-lived.
Once the F-117's existence was known, countermeasures were inevitable.
The first and only combat loss of an F-117 occurred over Serbia in 1999.
The Serbians employed a new tactic. They constantly moved their radar and missile launchers. And activated them for only very short periods. This made it impossible for U.S. planners to map the safe routes the F-117 relied upon.
A luck battery managed to acquire a lock and destroy the aircraft.
By this time, the F-22 Raptor, a true fighter aircraft,
incorporating far more advanced all-aspect stealth, had already made its first flight.
The F-117's legacy was not as an enduring platform, but as a revolutionary proof of concept.
It was the first true stealth aircraft, a weapon that fundamentally changed the calculus of war. It proved that invisibility was possible, forcing a paradigm shift where stealth is no longer a specialization, but an expected standard for all modern combat aircraft. Culminating in the interconnected hive mind doctrine of the F-35.